There are two definitions you need to know for acids and bases in IB chemistry. The first one is Bronsted-Lowry definition. They go after protons and they define acids as molecules or species that donate protons. Now, proton is a hydrogen atom stripped of its electron. Hydrogen has one electron, one proton. When you remove the electron, you're left with proton. So proton has symbol of H for hydrogen and plus charge. Bases, on the other hand, accept protons. H plus. For example, if you look at hydrochloric acid, HCl, when it reacts with water, water is forced to behave as a base. So this one donates its proton and H2O is accepting. It's behaving as a base. When you lose your H plus, you're left with the leftovers, chloride. And when you accept H plus, you form H3O plus, hydronium. Now, if you look at the reaction in reverse, you see H3O plus, hydronium is losing H plus or donating. Therefore, this is your acid, but we call it conjugate acid. If you look at Cl minus in reverse, is gaining H plus or accepting, therefore it's your base, and we call it conjugate base. And I describe conjugations in the next slide. Let's look at another example. Ammonia is a weak base. You should remember that and know that from now on. When it reacts with H2O, this time H2O is behaving as an acid. By definition, NH3 base accepts the H plus from H2O, forms ammonia. H2O is losing its H plus, forms leftover hydroxide. Reaction in reverse, NH4 plus, in order to come back to NH3, donates H plus, therefore it's your acid, conjugate acid. OH minus accept H plus to come back to H2O, therefore it's conjugate base. Now, one other definition comes to life at this stage. If you find a species or a molecule that some of the time behaves as a base and the other times as acid, it has dual nature in it, that's called amphoteric or amphiprotic. So amphiprotic or amphoteric is a molecule or ion that sometimes behaves as a base, the other times as an acid. So Bronsted-Lowry, they go after proton, which is H plus. Acids donate, bases accept. Now let's talk about Lewis acids and bases, which is a little bit more annoying. Lewis always studied electrons, and for him acids are deficient, or they rather accept a pair of electrons. And it's important, if you are forced to define it, to put the word pair. So you accept a pair of electrons, and you are also called an electrophile. You seek electrons. Now, bases to Lewis in terms of electrons were donators, or they donate a pair of electrons, and they are known as nucleophiles. They love positive charges or nucleuses. For sake of example, if you look at aluminum trichloride, aluminum itself only has 6 electrons surrounding it, therefore it's not octet stable, and it's deficient in electron. It can accept pair of electrons, therefore it's your Lewis acid. Now when it comes next to ammonia, for example, ammonia is rich in pair of electrons, so it's your Lewis base. Now this pair of electrons from ammonia, they have affinity for the aluminum, which is positively charged and very small. And what they are going to do is they react and they form a dimer, which is a molecule made out of 2 partners. So let me just satisfy electrons of chlorines. And then we usually show an arrow for the newly formed covalent bond between nitrogen and aluminum. Why an arrow? Because if you remember it, you studied it before. This is known as dative or coordinate covalent. Dative coordinate covalent. Meaning it's an unequal sharing. The pair of electrons belong to only one species. It's not shared between them equally. Another example, or a bunch of examples that you need to know in terms of Lewis acids and bases, are your transition metals. All transition metals are Lewis acids because they are very small and highly positively charged. So this is Lewis acid. If you bring it in vicinity of water, H2O. Now don't forget H2O has two pairs of electrons. It's rich in electrons. So that's your Lewis base. And what you form is a complex ion. I don't have much room, but I'm going to show 6 arrows surrounding this Fe. Each arrow is the oxygen's pair of electrons that are forming a coordinate covalent bond with the highly charged, positively charged Fe. And you usually put it in a bracket to get the complex ion across and the charge goes outside. So the complex ions are acid-base reactions in terms of Lewis definition of acids and bases. All transition metals are Lewis acids because they are deficient in electrons and they can accept pair of electrons. H2O, ammonia, not only they are Bronsted bases, they are also Lewis bases because they have pair of electrons to donate. Now, in order to get conjugations across, let's go to next slide. Conjugate simply means coupled or joined together. And a pair of acid and base conjugate, they differ by one hydrogen. For example, if you look at hydrocyanic acid, if you remove or donate H+, so I'm going to show it as subtraction minus H+, you form cyanide, Cn-. This is your acid, and this is your base version or pair. So this is acid-base conjugate pair. If you come back, cyanide plus a hydrogen plus, you come back to your origin, which is hydrocyanic acid. So HCN and Cn- are definitely acid-base, conjugate acid-base pair. Now let's just have a practice going here. So I have a bunch of examples. Now remember, by definition of Bronsted, if you are a base, you accept a H+. So you gain H+, and we put it as an addition. So NH3 plus H+ forms ammonium, NH4+. OH- plus H+ becomes HOH or H2O, no charge. They cancel each other out. HSO4 plus H+. Now you are sulfuric acid, H2SO4, no charge. Cn- plus H+, HCN. H2PO4- plus H+, yes, H3PO4, phosphoric acid. If you are being challenged in reverse, same thing, just apply the definitions and remember conjugations is just swap of one hydrogen. So acids, on the other hand, donate a proton, so subtract the H+ from acid and you have your conjugate base. HCO3- minus H+, you become CO3, your charge becomes 2-. H2O minus H+, your hydroxide, OH-, NH2-. Now this is a difficult case, you usually don't have it, but if you're forced to do it, you still have a hydrogen, remove it. So OH- becomes O2-, H2PO4- becomes HPO4, 2-. One other thing I want to work on and talk about is amphoteric, amphiprotic, one more time. Those that can accept and donate protons. So I have two examples I want to work. The first one, I go after sulfuric acid. It's diprotic, meaning it has 2 hydrogens that it can donate. Let it react with H2O. you will lose one hydrogen. HSO4 minus comes to life plus hydronium. Let's apply our definitions of Bronsted-Lowry acids and bases. So I'm acid, H2O is a base. On the other side, if you look at the reaction in reverse, HSO4 is gaining, so this is your base, call it conjugate base. H3O plus is conjugate acid. By the way, H3O plus is always acidic. You never have it as a basic, so you can always feel good and memorize it. Now HSO4 minus still has one hydrogen. Let it react with H2O and see what happens. Donate that, so you form sulfate, 2 minus, hydronium. Put equilibrium. I'm an acid because I lose. If you look at left versus right, I'm a base. Look at the reverse. This one is conjugate base, conjugate acid. Now can you find the amphoteric species in these two reactions? Hopefully you went after this, because now you're a base. It's not important if you're a conjugate base, you're still a base, and this is an acid. So HSO4 in this two reactions is behaving as amphoteric. I will do one other example so you have enough practice. Look at phosphoric acid, which is a weak acid. You usually find it in your Coca-Cola. It gives the sour taste. It reacts with water, loses one hydrogen at a time. You will form H2PO4 minus plus hydronium. So this is acid because I donate a base, conjugate acid. Let's go after the second hydrogen. So H2PO4 minus plus H2O. Another equilibrium, lose one more hydrogen, HPO4 2 minus plus hydronium. Name them acid, base, conjugate acid. The last hydrogen, you still can lose it. HPO4 2 minus plus H2O will give you PO4 3 minus plus H3O plus. Acid, base, conjugate acid. Now there are two species in this series of reactions that are amphoteric. The first one is H2PO4 minus. Here I'm a base, and in this reaction I'm an acid, so this is the first amphoteric. The second one is HPO4 2 minus. You're a base, you're an acid. You had your dual nature, therefore amphi or amphoteric, amphiprotic.